Hi guys, welcome back to the channel. Today we're going to do a quick exercise on Kangaroo physics, and we're going to test some mesh relaxation methods. We're going to first build our physics engine, and we're going to learn about what meshes are, how to work with meshes, and what we can do with the relaxated forms basically. So first of all, let me give you a quick rundown of what meshes are. If you're using Rhino 7, there's already a subdivision tool that is embedded, but we don't have those advanced mesh tools in Rhino 6, but that's not a big problem for this exercise. So most of you would know we work with surface tools. So I'm going to create a basic surface. This is a NURB surface, and this is a parametric surface. So when I turn its points on, you see that if I move any of these points, the data or the surface data, let's say, is interpolated between these points. So this surface has some degree input into it. So there is some interpolation between its control points. If I were to rebuild this, let's say we increase its point count and we increase its degree count. This of course affects how the data or the points are interpolated to define the NURB surface. And if I'm working with 4 control points in each direction, you would see that now they have these dashed lines in display, which means they're somehow parametrically correlated, and the data is two-dimensional. So if I select these groups of 4 points and move these up, you would see that there are some sections of this surface that are being interpolated as well. So these 4 control vertices define this type of Bezier curve here, and these 4 define this section here. And of course, all the remaining points affect how the surface topology is constructed. So if I move any of these points up and down, that will affect how the data flows along the surface, because we are directly manipulating the control vertices or the sections of this NURB surface. Now, what happens when I mesh this surface? So that's going to be our concern today. When I mesh this, Rhino gives me a default polygon mesh option, which basically affects how much resolution, let's say, we need to transfer to our mesh geometry. And if I'm working with this NURB surface and I want, let's say, an average mesh, there are also detailed controls here, which I'm not going to get into in this session. But if I were to resort to simple controls and select an average mesh and hit OK, now you would see that this geometry is now converted into a mesh geometry, and it's being approximated as close as possible. And if you were to look at what the mesh is doing and turn its control points on, of course you have a lot of different information. You have now points and faces compared to control vertices and interpolated parametric surface rendition. So in this case, if I were to choose any of these groups and if I move them, you would see that this actually distorts the geometry. It directly moves the vertices of the mesh. And these vertices are used to construct either quads made out of 4 control points, or triangles that are made out of 3 control points or control vertices. So the difference is that this gives us a reduced data structure that is formed out of indices of points and the faces that are defined by those points, whereas the NURB surface is defined by control points that are interpolated. So that's kind of the difference between a mesh and a NURBS in a nutshell. So a mesh has points, faces, and it might also store color data anchored to vertices, whereas in a NURB surface we have control points that control the topology or the curvature of the surface overall. Now we're going to work with meshes for this exercise, and the reason is because we're going to do some relaxated forms. So let's look at what those are, and we're going to also look at some Kangaroo tools for this exercise. So I'm actually going to begin by, let's say, building our physics engine first. I'm going to turn on my notes so that I don't mess this up. So let's say that we want to create kind of a cloth animation or something that is defined by a single surface, but we want to relax it. By the way, I forgot to mention, but for this exercise to work, you need to install both the Weaverbird components and the Kangaroo and the Kangaroo components as well. So you have to install both of these plugins to make this work. Okay, so let's get down to work. We are going to first of all look at what relaxation or how the relaxation works. So we are going to build a simple mesh. If you go to the Mesh Tools tab and click on the single mesh face, we're going to start by drawing vertices, and you can actually stop at the third one, which would be a triangular mesh surface, or you can keep going. So I'm going to create a pentagon type of shape, and this would actually be transformed when we are working with this algorithm. So what I want to do is create a 5 anchored surface that is relaxed with Kangaroo. So we're going to first load this into Grasshopper by using the mesh input. So right click here and do set one mesh. And you can see when I select these points on, you can see that there is actually no mesh surface that is defined by 5 control vertices. So a face cannot be defined by 5 vertices. So it has to have either triangles or quads. In this case, the mesh surface is automatically translated into a triangulated data. So you can see that we have 3 triangles defining the pentagon type of shape. And I'm going to hide this. Actually, let's make it a bit more interesting. So I'm going to turn the points on and move these vertices up and down so they all have different z coordinates. And we will try to turn this into a smoother shape using Kangaroo tool. So that will be the point of this exercise. So I'm going to hide my mesh, but you can see that we actually have polygonal data, right? So it's a polygonal representation of our mesh surface. In the next step, we are actually going to think about how we can build our Kangaroo engine. So the first thing I want to extract is our mesh edges. So if you type in mesh edges, get all the mesh edges of our surface. So you can see that when I do it to this mesh, we only get the 5 surrounding bordering lines, but I actually need a bit more than that. So just having this topology is actually not enough. So what I'm going to do is subdivide this further to define more triangles. So if you have loaded the Weaverbird tools and go to subdivision, you can work with any of these, but for this exercise, I'm going to work with loop subdivision. So what loop subdivision does is it takes in a mesh and it actually subdivides it into more triangles. And this is kind of a recursive operation. So if you go to the mesh tab, analysis, and let's say face boundaries, you can actually look at what's happening after the subdivision. So initially we have this initial boundary. Actually we might be able to do face boundaries, I think should work, but after one division, you can also check what's happening with the mesh. So initially we had 5 vertices and 3 faces, the 3 triangles. After one subdivision, we got 12 vertices and 12 faces. And if I were to check the mesh faces here, you can see that we have more triangles formed. So if I bake this mesh, you can see that these are separate mesh faces, but you can see that the initial triangles are further subdivided into 4 triangles each, right? So there was a triangle going this way, another triangle going the other way, and all of them have been subdivided using the loop subdivision. And if you look at the symbol of loop subdivision, what it does is it takes the midpoint of all the mesh edges and it creates 4 triangles using those central points. There's also another option under the loop subdivision, which is how to treat naked edges. A naked edge is basically a bounding condition of the mesh. So in our case, the naked edge would be the outer polygon of the mesh. So let's say I have, I'm defining all the way up to 3 loop subdivisions. You can see that this is a recursive operation, so it can add more triangles to our division. And if I change how to treat the naked edges, let's say if I give 0 here, then the initial or the resulting subdivision would actually be constrained to the boundary condition. So if I keep this as 0, you can see that there are 3 triangles. When I hit 1, the midpoints of the subdivision are calculated and we get this sort of loop subdivision where we have 12 triangles total. And if I keep doing this, more triangles will be added. It doesn't do it after 3, but the third level will be enough to create triangles for our relaxation to work. Why are we creating these subdivisions? Is because in order to create some geometrical operation here, like sagging behavior, you actually need to create more faces. You need to create more geometry, right? So that's our goal. And after loop subdivision, we actually don't need the mesh face boundaries, but I'm just going to keep them up there so that we can see where the geometry is. The next phase is to build our physics engine. So for this one, we need 2 things. We need forces, which are going to come from springs. So springs are located under the Kangaroo tools, forces. And the other thing is the Kangaroo physics. So if you go to this tab, Kangaroo physics, I think this would work. Yeah, this would work. So for the springs, we actually need to input a few things. We need to input, we need to define the mesh edges, so you can actually grab the first and the second curves, which are, let me see here. We actually need to get the looped version. So we need to get all these curves that are formed for our subdivided mesh. Then we calculate their length. And in order to relax them, we actually need to define some sort of a rest length or target for these curves. So remember that they have some predefined length, right? So in order for it to change, we need to give it some sort of rest length. And that rest length is going to affect or turn all of these lines into springs. So they're going to be a bit more elastic. So they're going to be able to move basically. And that's how we're going to simulate the physics behavior. So if I multiply this length, let's say with 0.8, what that means is I'm giving a rest length of 8%, 80% for this curve, and I'm going to input that connection. And for the stiffness, you can have a bunch of variables or values. So you can start with 500. 500 is pretty stiff, but the lower this value is, the more elastic or flexible your system will become. So I'm going to start with, let's say, somewhere around 300. And the next phase is to create some anchors for ourselves. So what are those anchors? We actually need to define them. So there could be multiple ways of defining them. So if you type in mesh or naked vertices, so this naked vertices are located under Kangaroo 2 under mesh. So if you feed in your initial geometry, this will give you clothed and naked points. And let's look at what those are. So if I were to select the clothed points, the clothed points means that these points rest within the topology of the mesh, whereas the naked points define the bounding condition or the edge of our mesh. Remember that the geometry is polygonal and all of these points define triangles that are flat. So among these naked boundaries, let's say we want to anchor these 4 or 5 corner vertices. So there are a bunch of ways you can actually input them. You can grab them one by one from this list, or you can be more pragmatic. You can just bake these and grab them manually in Rhino, which will be a bit more easier. So if I were to define a point input here and do set multiple points, choose these corner vertices, these will be where my mesh would be anchored, and those points will not move, but all the remaining points will move and create that type of sagging behavior. And so the other thing is these would go into my anchor points for the Kangaroo simulation, whereas my force objects would be coming from the springs. My geometry will be coming from our subdivided geometry, and we will have a simulation reset and a timer. So if you go to, you can also type in timer here. A timer is basically something that controls how fast a simulation is run. So this you can tie it up by clicking here and connecting it to the Kangaroo physics simulation, and you can define an interval, let's say 100 milliseconds. And that will define the rate of update for this plugin to work, because we're going to run a simulation. And the last thing I need is a Boolean toggle, which I'm going to feed into simulation reset. I'm going to go back there. So this actually has only 1 point. Let's actually put more. So right click here, set multiple points, 1, 2, 3, 4, and 5. So that should have now 5 reference points, which are going to hold our cloth in position, and all the remaining points will be in action. So they are going to move according to these springs that we defined with a rest length parameter and a stiffness parameter. So I'm going to hide some of this data. So let's hide this data, and for the geometry output, let's put a mesh there. And I'm going to hide these guys as well, so we get to see what's going to happen with our mesh. And I'm going to also connect face boundaries for the resulting mesh so that we see how it behaves. You can hide or disable those points as well. So this is the surface. These are our anchor points that are holding the cloth in 5 positions. And when I hit false here, you can see that the mesh is being relaxed, and basically there is some tension being formed between these surfaces. So it's kind of like a tensile structure, and we can actually simulate a lot of the behavior here. So if I show the initial geometry, if I grab these points, let me see. We don't have the initial mesh, I think. Let's see, the mesh is here. Yeah, so let's see, there is one mesh. Okay, there is a mesh there. So if I grab this point and move it up, you can see the simulation also moves along with it. And that's what's cool about this workflow. So you can anchor the vertices on these corners, and you can create a lot of different interesting surface structures with this as well. So I can combine different types of methods. Maybe these 2 points are on the ground and these are up, and they could be held by cables or other types of geometry. But this is kind of a really nice way of modeling surface behavior or the relaxation behavior using single meshes. And let's say if you want to export or create this model, you can also use some Weaverbird tools. So basically we have the mesh geometry that is generated now. If you need more resolution, let's say we want to output this as a mesh net, then I can go to Weaverbird. Before I do the framing, you can also do another loop subdivision to this. So do another loop subdivision and create more meshes. But this time, let's keep it at 2, which gives me enough triangles. And if you look at the corners, you can see that if we don't anchor the fixity of the naked boundary, it could become more smoothed out, right? So this point will lose its grip, and you can control how that's going to be done if you change the setting here. So if you set this to be 0, then the naked boundary will be fixed so that the triangle will be fixed there. And using this mesh, what I'm going to do is grab onto this and then go to transform, picture frame, and I'm actually going to give it some thickness. So default is 5. Let's make it 20 is a bit too much, but let's keep it at 12. So if I hide all of these, you can see that that creates kind of a hollowed out mesh net, right? So I can bake that form, and this is a geometry that we achieved by modeling the mesh using physics simulation, right? So this is kind of a relaxed form that we computed or calculated. So that's one way of doing it. I'm also going to show you another way, which is a bit more different, but the workflow would be somewhat similar as well. So we can do single surfaces, but we can also do volumes using Kangaroo. So how do we approach the issue of volume? Remember that I have defined the mesh that I wanted to relax. So the mesh could be longer, or it could be made out of other primary elements. Like I can have quads, triangles forming up a more compound shape. But for volumes, we actually need to build it using other types of geometry. So for instance, I'm going to hide this part, or let's actually disable that part. I'm going to make another copy of this structure so that we don't lose the initial approach. But let's say that we go to Mesh Tools, and here there's something called Mesh Box. So using this Mesh Box, we can also create some volumetric applications. So for instance, if I click here and then click on this volume, now we can actually build some sort of topology that can have bifurcations in it as well. So let's say that we're going to have something that has this sort of topology. And remember that we are working with meshes, so these vertices need to be snapping to each other. So that's kind of the essential part. And now they're distinct. But you can select all of them and do mesh Boolean union. And now these are joined. So I'm going to create a relaxed form, like a net in which we can go through, right? So this is going to be kind of a volumetric relaxation exercise almost. So I'm going to delete these faces, and the remaining faces I'm going to join them. So imagine that this is a tunnel where we can enter, and we will have 2 different exits, right? But I'm going to make it a bit more interesting. So I'm going to go to Standard tab, turn on these points, and we're going to play around with the location or the orientation of these points, so we can turn it around a bit. But the way I'm doing or approaching this task is, when I'm adding more geometry, I'm also thinking about how it will connect the topology, right? So imagine that this is kind of like a branching geometry, so you need to orient the mesh faces in such a way that the geometry will be tessellated in the right manner. So now let's say that this is the second geometry. I'm actually going to hide these points as well. Let's see, these points are here too. I'm going to actually clear that data. Now, this is a volume. So what I want to do is first load it here, set one mesh, and load our geometry. And before I run the simulation, I'm going to disable Kangaroo and see what's happening when we actually propagate this geometry. So you can see already before we run the physics simulation, this actually gives me kind of a relaxed form with loop subdivision. So if I keep it at 0 and smooth naked edges at 0 as well. So by relaxing it, you can see that we are actually defining some sort of relaxation, but this is a geometric relaxation. It's not physics-based relaxation. So let's make it a bit more interesting. Let's actually move it around a bit, maybe rotate it as well. And this guy, let's move it down, rotate it too. So they can face different directions. They can actually have different types of, you can also play around with these vertices as well. So that will change the type of geometry computation that you're going to have, right? So let's say I have a shape like this. And this part, let's actually make it a bit more higher like this. Okay. So I don't know how it's going to work, but or what's going to generate. But let's say that this is the geometry I want to output. All right. Now, now that we have that done, you can see that after the relaxation, it's a bit irregular, right? So if I bake this form, the geometry is not looking smooth. So you can see that it's a bit distorted right now. So that's why we need a tool like the Kangaroo to actually smooth this out for us. So how is it going to smooth it out? Well, this already has some naked points. So after the subdivision, if you turn on these naked points, you can see that it grabs onto the deleted faces. So that's the reason why I'm deleting those faces. So if I don't delete them, this tool would not recognize them as naked points. A naked point is basically the bounding edge of the mesh, right? So if it's a closed topology, then we need an open face where the mesh would be open so that we can grab its naked edges or naked points. And I'm going to input these directly as anchor points, so you can put them here. And I'm going to keep the springs as it is. Turn on the Kangaroo simulation. Now turn this to be true. You can see it gives me already some computation. I'm going to hide this loop. And all I have to do is turn this to be false. And now my physics simulation is running, and you can see that we are now achieving a bit more smoother forms, right? So this is still running. I'm going to keep my screen still, but you can see that it is still computing with this 100 milliseconds. So if I increase this interval to be 200, it's going to give me a faster computation. And if I'm satisfied with the result, all I have to do is bake this end result. And now we can compare those two forms. So this was our initial geometric subdivision. And this one was more like a computed, relaxed, volumetric mesh. So you can see that this is actually giving us a lot more smoother geometry. So that doesn't depend on the orientation of your pieces. And it gives us kind of a nice geometric output as well. So using this approach, let's recap what we have done. You can actually generate relaxed forms that can be based on single surfaces where you anchor them on individual points, and then the surface can behave according to the relaxation. Or you can create more volumetric approaches and use anchoring points around the naked edges and create these sorts of connected shapes. And I'm looking forward to what you can come up with. So if you have any questions, feel free to write under the comments below. Okay, and I'll see you guys next week with another tutorial. Take care.